folks, welcome to another set of Chemistry 2 video notes. Today we're going to cover Chapter 15, which is all about acids and bases. The topics in this chapter cover what electrolytes and non-electrolytes are, the difference between weak and strong electrolytes, what acids are and how to tell if they're weak or strong, what bases are, a more updated definition of acids and bases, what weak bases are, water and its tendency to dissociate into ions, the pH scale, and buffer solutions. That's a lot to cover, so let's get started. The main goal of this chapter is to talk about acids and bases. Historically, acids and bases were classified by simple testable properties. For instance, anything that tasted sour, turned litmus paper red, and was corrosive to metals was considered an acid. Anything that tasted bitter, turned litmus paper blue, and was slippery in aqueous solutions was considered a base. I'd like to point out that in the early days of chemistry, safety was not quite as understood as it is now. So please don't ever taste a solution to see if it's an acid or a base. Any solution that didn't fit into one of those two categories was just considered neutral. Litmus is a plant-based indicator. Soaking a piece of paper in litmus, drying it out, and then placing that paper in a solution could result in a predictable color change, red for acids and blue for bases. We call that an indicator because it indicates whether the solution is an acid or a base. Before we can understand the definitions of acids and bases at the molecular level, we have to understand another classification scheme, electrolytes and non-electrolytes. This was one of the first classification schemes for chemicals that was able to be described at the molecular level. Originally, electrolytes were defined as substances that could form aqueous solutions that conduct electricity. Non-electrolytes were those that could not conduct electricity in aqueous solutions. For example, when you dissolve sodium chloride in water, it's able to conduct electricity. The aqueous solution of sugar, however, does not allow electrical current to flow through it. Chemists wanted to figure out why this was the case. Michael Faraday proposed the idea that in order for electrical current to pass through a solution, there must be some mobile charged particles in the solution. He called these particles ions. A few decades later, a Swedish chemist named Svante Arrhenius took that definition a little bit further and said that Faraday's ions were produced by the solute particles in a solution, not just dissolving, but dissociating into ions. Dissociation is when solute particles split up into their separate ions. For example, our sodium chloride would dissociate into sodium cations and chloride anions. The sugar molecules only dissolve into individual sugar molecules. They don't split up any further than that into charged particles. This explains why salt water can conduct electricity, but sugar water cannot. All soluble ionic compounds will dissociate into ions. Some of the more polar covalent compounds, such as hydrogen chloride, hydrogen iodide, hydrogen bromide, and ammonium chloride, will also dissociate into ions. Most covalent molecules, however, do not dissociate, they only dissolve into uncharged molecules. With Arrhenius' work, we can now expand our definition of electrolytes and non-electrolytes to say that electrolytes are substances that, when dissolved in water, produce ions which allow an electrical current to flow through the solution. Non-electrolytes do not produce ions when they dissolve in water, and therefore do not allow for the flow of electrical current. Electrolytes can be classified as strong or weak. If all of the particles of a solute dissociates into ions, we say it dissociates completely, and it's called a strong electrolyte. For example, hydrogen chloride will dissociate into H+ and Cl-. This reaction goes to completion, as the rate of the forward reaction is much, much greater than that of the reverse reaction. When HCl is done dissolving, we're left with no undissociated HCl molecules, only the hydrogen and chloride ions. To be more accurate, as you can see down at the bottom here, we should include water in our reaction. In aqueous solution, hydrogen ions do not exist as hydrogen ions by themselves. They latch on to any nearby water molecules to create the hydronium ion, or H3O+. So for accuracy, we should include water and hydronium ions in our equation for the dissociation of HCl in water. A weak electrolyte is one that only partially dissociates, or only some of the solute particles turn into ions. This reaction does not go to completion, and it's considered a reversible reaction. For instance, the weak electrolyte HF will dissociate into hydrogen and fluoride ions, but most of the HF molecules will stay undissociated. Our equilibrium for this reaction lies to the left. To help illustrate this, we might draw the reverse arrow a bit longer than the forward arrow on this reaction. So why is this important? Great question. When we dissolve a strong electrolyte such as HCl in water, it completely turns into ions. The more ions we have in our solution, the more electrical current can be carried through the solution. Therefore, our conductivity meter here will shine brighter with more ions in the solution. Since most of the HF molecules stay as molecules, only a few ions are produced. Ions are still produced, so it's still considered an electrolyte, but based on the brightness of the bulb, it's clearly not as good at producing ions as HCl was. Like I said, we need to understand electrolytes before we can talk about acids and bases. Why is that? Well, according to Arrhenius, acids are electrolytes that produce hydrogen ions, or rather hydronium ions, in water. A strong acid, just like a strong electrolyte, will completely dissociate into ions, and a weak acid will only partially dissociate into ions. The main difference here is that acids don't produce just any old ion. They must specifically be able to produce H+ ions. Hydrogen ions are nothing more than protons, so we can classify acids based on how many protons they have to give. For instance, HCl has one proton to give, so we call it a monoprotic acid. H2SO4 has two hydrogens to give, so it's called a diprotic acid. You can guess what a triprotic acid looks like. It's important to note that having more hydrogens to give doesn't mean that an acid will produce more hydrogens, or that it'll be stronger. If we write the equilibrium constant expression for the H3PO4, each time it loses an H, we see the equilibrium lies further to the left. In other words, it's happy to give up that first hydrogen, but it's a little bit harder for it to give up the second, and even less favorable for it to give up its third hydrogen. The KEQ value for an acid can tell us how well the acid does at dissociating, and therefore how strong the acid is. The larger the KEQ, the stronger the acid is, because the more ions are produced. If the KEQ is greater than 10 to the third, the dissociation goes to completion, and we call it a strong acid. Acetic acid is a good example of a weak acid. Notice in the picture here, at equilibrium, we have plenty of undissociated acetic acid molecules in solution, and only a few hydronium and acetate ions. For our purposes, you can assume that all acids are weak acids except for these 7. Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, chloric, and perchloric acids are all strong acids. You should commit these 7 strong acids to memory. Remember, the historical definition for a base is that it's bitter, it turns litmus paper blue, and it produces slippery solutions. As we started to understand acids more, we're able to add another characteristic to the properties of a base. When you add a base to an acid, it reacts with the acid and kills it off, or neutralizes it. This is known as an acid-base neutralization reaction. When an acid and a base neutralize each other, water is always produced. These neutralizations often produce neutral solutions that taste salty. If we think about the reaction of hydrochloric acid and sodium hydroxide, it produces water and sodium chloride. This is essentially the same as if we were to dissolve some table salt in water. As defined by Arrhenius, a base is any electrolyte that contains a metal ion and a hydroxide group, and produces hydroxide ions when dissolved in water. These take the general form of MOHN, with M being the metal ion and N being the number of hydroxide ions needed to balance the charge of the metal ion. All group 1 hydroxides, such as lithium hydroxide or potassium hydroxide, are strong bases, because all group 1 salts are completely soluble. In AP chemistry, we pretend that all group 1 and 2 hydroxides are strong bases, even though our solubility rules state that barium hydroxide is the only group 2 hydroxide that's more than just sparingly soluble. So, even though it's not completely accurate, we're going to follow those same rules here. You don't have to memorize a certain amount of strong bases, just assume that all hydroxides of any group 1 or 2 metal are strong bases. Arrhenius' definition works great in most cases, but not all of them. For instance, ammonia, which doesn't even have an OH group on it, can also neutralize acids. 2 scientists, Bronsted and Lowry, both independently from each other, came up with a new definition for acids and bases. This definition states that acids are anything that can donate a proton, or an H+, and bases are anything that can accept a proton. All bases, including those that have hydroxides, must have a lone pair of electrons on them in order to accept a proton from an acid. Of these three molecules here, pH3 is the only one that can act as a base because it's the only one with a lone pair of electrons in its Lewis structure. Even by Arrhenius' definition, ammonia is still a base. When in water, it'll accept an H+ from the water, leaving water as just OH negative. The Bronsted-Lowry definition does help us understand the reaction better, knowing that water acts as an acid by donating a proton, and ammonia acts as a base by accepting that proton. The Arrhenius definition still holds true, though, since ammonia does produce hydroxide ions in water. Ammonia, the carbonate ion, and the acetate ion are just a few examples of weak bases. You might notice some of these weak bases are just weak acids without one of their H's. For instance, acetic acid minus its H is just the acetate ion. This will become important for our last section. We can measure the strength of our bases based on their KEQs just like we did with acids. The larger the KEQ, the stronger the base. If you'll remember the solubility product, or the KSP from our last chapter, that was the same thing as the KEQ for our sparingly soluble substances. The same kind of thinking works for acids and bases. The KEQ for an acid is known as the acid dissociation constant, and it's labeled as Ka. The KEQ for a base is known as the base dissociation constant, and it's labeled as Kb. The acidity of a solution can be measured by how many hydronium ions are in the solution. Water by itself does have some hydronium ions in it. This is because water will dissociate into hydroxide and hydronium ions, as you can see in this reaction here. This is called the auto-dissociation of water. In this reaction, two water molecules, one acting as an acid and the other acting as a base, will form a hydroxide ion and a hydronium ion. When this reaction reaches equilibrium, it lies pretty far to the left. If we're to write the KEQ expression, it'd look like this. Since the equilibrium lies so far to the left that the concentration of water changes only a negligible amount, we consider the concentration of water to hold constant and just move it over to the KEQ side, which is full of constants. This gives us the Kw, or the auto-dissociation constant of water. Kw is equal to the concentration of hydroxide ions times the concentration of hydronium ions, and, like any other K we've seen, can change with temperature. For our purposes in this class, we're going to stick with these solutions at 25 degrees Celsius, where the Kw always equals 1 times 10 to the negative 14. If we do a little bit of math, we can find that at 25 degrees Celsius, pure water will have a hydroxide concentration of 1 times 10 to the negative 7 molar, and a hydronium concentration of the same. This means that for every liter of water, there's about 0.000007 moles of hydronium and hydroxide. Not a lot, but definitely not zero. For pure water, or any neutral solution, the hydronium and hydroxide concentrations are equal to each other. Anytime your solution has more hydronium than hydroxide, or more H3O than AOH, it's an acid. When you have more hydroxide than hydronium, it's a base. It's important to note that a solution being neutral does not mean that there are no hydronium or hydroxide ions. Even pure water has hydronium and hydroxide ions in it. Neutral just means that the concentrations of each of those are equal to each other. Since Kw is a constant, when you increase the concentration of hydronium or hydroxide, the other ion's concentration must decrease. We'll be able to see that a bit more on a chart on the next slide. So here we are near the end. A common way to describe the acidity of a solution is by talking about its pH. pH stands for the potential of hydrogen ions. Instead of looking at the molarity of hydrogen ions in those crazy scientific notations, we can use the logarithmic function to convert it to a scale that fits from 0 to 14. To do so, we simply take the negative log of the hydronium concentration. The higher the H3O plus concentration is, the lower our pH will be, and the more acidic our solution will be. We can do all of this math pretty easily on a calculator, but I find that life is simpler if we just know what math we're doing. So let's talk about log. The log button on your calculator is the log base 10 function. It simply asks the question, to what power must I raise 10 to get this number? For instance, the log of 1 is 0 because 10 to the 0 is 1. The log of 10 is 1 because 10 to the first is 10. The log of 100 is 2 because 10 squared is 100, and so on and so forth. This is pretty simple for any number that's just 1 times 10 to the something. In those cases, the log is just the exponent on 10. If I did the log of 1 times 10 to the negative 7, the hydronium concentration in pure water, I get negative 7. That's why we do the negative log of our hydronium concentration, so we can get pH values between 0 and positive 14. You can always use a calculator on this for class, but if you ever find yourself without a calculator and you want to quickly estimate the negative log of a concentration that isn't just 1 times 10 to the something, it's easy peasy lemon squeezy. All you do is take the exponent on 10, flip its sign, and say that the pH is equal to 1 less than that plus some decimal. For instance, the negative log of 2.75 times 10 to the negative 8 would be somewhere between 7 and 8. I take the 8 from the exponent on the 10, reduce it by 1, making it 7, and then I know it's like 7 point something. Feel free to grab a calculator and test me out on that. When we calculate the pH, that number tells us whether we have an acid or a base, or if our solution is neutral. If the pH equals 7, our solution is neutral. If it's less than 7, it's an acid, and if it's more than 7, it's a base. If you wanted to find the hydronium concentration from the pH, you simply undo the negative log base 10. If log was what power do I have to take 10 to get this number, then you simply take 10 to the power of that number. So in this case, since we did negative log of H3O plus to find the pH, then we do 10 to the negative pH to find the H3O plus. All of these calculations are the same for the hydroxide concentration in the POH. POH is a much less used scale, but one that can save us some time in the long run when we're doing these conversions. If we did a little bit of extra math, which I'd be happy to show you later, we can also show that the pH plus the POH is always equal to 14 at 25 degrees Celsius. To sum up all of that math we just learned, here's a handy chart that'll help you convert between the hydronium or H plus concentration, the hydroxide concentration, the pH, and the POH. Just follow the arrows to get from one point to another and complete those calculations as stated. pH is a very important concept. For instance, the pH of our blood sticks around 7.4. If it drops much lower than that, say even down to 6.8, we're at high risk for a coma or even death. Rain, since it mixes with carbon dioxide in the air, produces carbonic acid, and it usually has a pH of about 5.6. In particularly polluted atmospheres, it can react with other chemicals, such as sulfur dioxide or the sulfite ion, and it produces sulfurous or sulfuric acid. This can bring our pH down a lot, like as low as 3. Any rain with a pH between 3 and 5.6 is called acid rain, and it can damage vegetation, wildlife, and infrastructure. Fortunately for us, blood is much better at resisting changes to pH than water is. This is known as its buffering ability. Any solution that has a buffering ability is called a buffer solution, or just a buffer. Buffers are made up of a weak acid and a weak base, and then its conjugate pair. So what is a conjugate? Some synonyms for conjugate are to marry or be coupled. A base is coupled with its conjugate acid, and an acid is coupled with its conjugate base. An acid with its conjugate base, or a base with its conjugate acid, make up a conjugate pair. If you look at a list of conjugate pairs, you'll notice that a conjugate acid is just the base with an extra H on it, and a conjugate base is just an acid that's missing an H. In other words, the conjugate acid is what's formed when a base gains a proton, and the conjugate base is what's formed when an acid loses a proton. We can create a buffer solution by mixing a weak base or acid with a salt of its conjugate. Why do we use weak acids and bases? Because the goal is to have two species in our solution, one that can neutralize incoming hydroxide ions, and the other that can neutralize incoming hydronium ions. Strong acids and bases dissociate completely and stay that way. For instance, HCl splits up into H plus and Cl negative. H plus could counteract incoming hydroxide molecules, but the Cl negative will never react with incoming hydronium ions to produce HCl and water again. Remember, the HCl dissociation equilibrium lies so far to the right that it never works in the left direction. Since weak acids and weak bases exist at dynamic equilibrium, we use those. Acetic acid, for instance, will dissociate into H plus and the acetate ion. The acetate ion is just happy reacting with any incoming hydronium ions to produce acetic acid again and water. This is well illustrated by these sharks in this beaker. Having both a weak acid or base and its conjugate base or acid present in a solution allows any incoming acids or bases to be neutralized without affecting the pH of my solution very much. This is because the conjugate base of a weak acid is a weak base, meaning they both can exist at appreciable amounts at equilibrium, which means we have acids and bases present and ready to neutralize any incoming acids or bases. Buffer solutions can only buffer so much. They can take on small amounts of strong acids or strong bases, but once all of the weak acid or weak bases present are used up in the neutralization, the buffer system's capacity has been reached, and it no longer resists changes to its pH. It's important to note that buffers do not cancel out pH changes completely. They only resist those changes. If I add a strong base to a buffer solution, I'm going to use up some of my weak acid molecules to neutralize it. Since I'm taking away the weak acid molecules from my solution, that's going to raise my pH because I'm reducing the number of acid molecules in my solution. It raises it just a little, not a lot. Well, that's all for today, folks. As always, if you have any questions, be sure to ask.